Welcome to Oddly Real. I'm Nem Stefanovic. We experience the effect of a force as a push or a pull. But what exactly happens at the lowest levels of reality to produce this effect? How do particles interact to transmit a force? There are force fields that permeate space all throughout the universe. When two particles interact with each other, they disturb these fields. The disturbance carries energy and momentum in the form of a force-carrying particle. The electromagnetic force-carrying particle is the photon, and the strong force particle is the gluon. The weak force has three kinds of force-carrying particles: two charged W particles, W plus and W minus, and the neutral Z naught particle. Interestingly, these force-carrying particles tend to interact behind the hidden veil of the energy-time uncertainty principle. Energy is borrowed from space itself to facilitate the interactions. Strangely, particles don't just interact in one simple way. There are many very strange interactions, all of which appear to happen together to produce the final observed results. We can never see what happens inside the particle interaction region due to nature's restrictions via the uncertainty principle. A measurement of the interacting particles would interfere with them, thereby altering the outcome of the experiment. Since we cannot measure these particles, in many ways they're not technically real. We call these ephemeral particles virtual particles. There is a theoretical prediction that all of these forces unite to have a similar strength at very high particle interaction energies above 10 to the power of 14 giga-electron-volts. This has inspired many physicists to search for a grand unified theory, or a GUT, that could help explain all of the observed forces as manifestations of one single force. Take two particles, A and B, that interact with each other. The interactions can take a variety of forms, such as scattering to repel each other, attracting together, or even annihilating each other. We know the energy and momentum of the two particles prior to their interaction. We're also able to measure the resultant energy and momentum of the particles after the interaction. However, we are not able to see exactly what happens at the point of interaction between the particles. This would require taking a measurement, and the act of measuring the particles would change the interaction itself. There's a certain amount of uncertainty that we have to accept as part of the process. This uncertainty isn't due to a lack of accuracy of our measuring devices, it's a fundamental limitation imposed by nature, which we call the uncertainty principle. We cannot simultaneously know both the position and momentum of a particle to any arbitrary degree of accuracy. However, we are able to imagine the different possible interactions that could occur within this region of interaction, along with their probabilities. It's common to refer to this region as the bubble of ignorance. What actually happens in this region is complicated, and not something that we can explain simply using classical notions of physics. Particle interactions are governed by the laws of quantum mechanics, which are strange and unusual compared to our daily experiences. For example, consider two electrons that approach each other and are scattered away. What actually happens between the two particles to make them recoil from each other? One of the simplest possibilities is that one of the electrons emits a photon, which is absorbed by the other electron. This exchange of energy and momentum causes the two particles to deflect away from each other. However, this is very strange. How is it possible for an electron to emit a photon? In this situation, there isn't any additional energy that the particle can use to produce this photon. Where does this energy come from? Incredibly, the source of this energy is the vacuum of space itself. In simple terms, the energy is borrowed for a very short period of time. This can happen due to the energy-time uncertainty principle. The energy-time uncertainty principle gives us a criteria for when we're able to observe and have knowledge about the energy used over time for a process. If the energy used and the duration of its use is less than the threshold provided by the Planck constant, the process becomes hidden under the energy-time uncertainty principle. Additionally, there's a trade-off between the amount of energy borrowed versus how long it can be kept when it's under the uncertainty threshold. If we borrow a lot of energy, for example, to create a particle with mass, that energy must be returned within a very short period of time. Alternatively, if a particle is created that requires less energy, like a photon, it can be utilized for longer. In fact, this behavior is one of the reasons why certain force-carrying particles can act over long ranges, like the electromagnetic force, versus others that are short range, like the weak force. On a side note, the force-carrying particles for the strong force are called gluons, and they are massless, yet they only interact at extremely short ranges, around 10 to the power of minus 15 meters, or around the diameter of a proton. Why is the strong force short range? In this case, when large amounts of energy are built up within the strong force field, it tends to break up to produce quark-antiquark pairs rather than gluons. But wait a second. One of the most basic principles of all of science is that energy is neither created nor destroyed. If we can borrow energy out of the vacuum, seemingly out of nothing, doesn't that violate the law of conservation of energy? Well, astonishingly, it actually doesn't. Recall that we can only make measurements of particles before they interact or after they interact. These particles are all well behaved and the law of conservation of energy is always obeyed. The interactions that take place within the bubble of ignorance are not observable by us, since they are hidden under the veil of the uncertainty principle. In a true sense, these particles are not strictly real. What I mean by that is that nothing in our universe is part of reality unless it is measured or observed. This is why these particles that fluctuate in and out of existence beyond our view are referred to as virtual particles. So far, we've looked at a single example of a photon exchange between two scattering electrons, where one electron produces a virtual photon that transmits energy and momentum to another electron, resulting in the two electrons recoiling away from each other. This is also not a physical reality, but a contributing factor for it. This is just one piece of a much more complicated interaction between the two particles. For example, the two electrons may exchange two photons between each other in the scattering. Or in another example, an electron may emit a photon only to eventually reclaim it. None of these diagrams are a specific outcome. Instead, the behavior of the particle interaction is the combination result of all of these effects. However, the more complicated the scenario, the less it will actually contribute to the final outcome of the particle interaction. Here's another strange scenario that we have to consider for the interaction between an electron and a positron. Assume each particle is moving at the same speed but in equal and opposite directions, so their net combined momentum is zero. When they collide, they annihilate, producing a photon. However, a photon with zero momentum is stationary and not moving at the speed of light as we would expect. This photon has mass. However, the situation is quickly remedied as the photon quickly converts itself back into a particle-antiparticle pair. Again, many scenarios like this would need to be factored into our calculations to ensure that we got an accurate result. Electrons, positrons, and photons interacting with each other is the basis for the description of particle interactions for the electromagnetic force. This quantum mechanical description is called quantum electrodynamics, or QED for short. This is also the most accurate physical theory that has ever been developed. For example, this has been used to describe the magnetic properties of an electron to an accuracy that is valid up to 1 part in a trillion. Given its success, the same principles of particles interacting via exchange of force-carrying particles was also extended to the strong and weak forces. In the case of the strong force, its quantum mechanical theory to describe its forces and particle interactions is called quantum chromodynamics, or QCD. QCD is more complicated than QED for the electromagnetic force for a number of reasons. First, the quarks in QCD have one of three different colors, which are equivalent to charges, but for the strong force. The force-carrying particle for the strong force is called the gluon, just like how the force-carrying particle for the electromagnetic force is the photon. However, gluons are also colored, unlike photons in QED, which do not possess charge. Thus, gluons also feel the strong force. Additionally, quantum chromodynamics puts more importance on more complicated Feynman diagrams for their contribution to the final interaction result. This is the opposite of QED Feynman diagrams, in which complexity reduces its contribution of the diagram to the final result. This is a difficult theory to work with in practice. However, when interaction energies between the particles are high, meaning the quarks and the particles can get closer together, then fewer Feynman diagrams are required to check the results. There's an amazing story behind the theory of the weak force and how it transmits force through particle interactions. Incredibly, its mathematics was so similar to QED theory that scientists were able to link both theories together to create one single unified theory for both electromagnetism and the weak force, called electroweak theory. This was essentially a rigorous framework demonstrating that the electromagnetic force and the weak force were really manifestations of one underlying force. A Nobel Prize was awarded for this work in 1979. Superficially, the weak force seems very different from the electromagnetic force. It converts particles to other kinds of particles. Additionally, it's an extremely short-range force, only taking effect at ranges of 10 to the power of minus 18 meters or so, much smaller than the diameter of a proton. The electromagnetic force is long range and applies over unlimited distances. Moreover, the weak force can also act between neutral particles, whereas the electromagnetic force only applies to charged particles. It was clear that to model the weak force in a similar way to quantum electrodynamics, there had to be three types of force-carrying particles: the charged W plus and W minus particles, and the neutral Z naught particle. Strangely, these particles were predicted to be inherently massless, in which case the weak force would also have an unlimited range of interaction. However, this is clearly not the case. In order to explain the discrepancy, it was proposed that there was actually a new field throughout the universe that interacted with the W and Z particles in space. This field is called the Higgs field. The W and Z particles exchange energy with this field, which results in the particles acquiring mass. One simplified way to imagine this is that the Higgs field acts like a drag for the W and Z particles. Amazingly, the addition of the Higgs field described the Z particles in two distinct forms: the familiar Z naught particle, but also a photon. The theory predicted the unification of the weak and the electromagnetic force. If this all sounds too convenient, the theory also predicted specific testable predictions, like how the Z naught particle would allow neutrinos to interact with other particles. This was experimentally validated to be true. Finally, modern-day physics describes particle exchanges as not just the transmission of discrete force-carrying particles, but as disturbances in the underlying force fields. In other words, photons, gluons, and the W and Z particles can actually be thought of as ripples in the electromagnetic, strong, and weak fields, respectively. Two particles come together, and their interaction produces a complex disturbance in the underlying force fields. The force-carrying particles are just a convenient representation of this disturbance. But what does it mean for classic particles like the electron? In fact, we can describe these particles as disturbances in a field as well. For example, the electron is equivalent to a disturbance in an electron field. This approach also innately describes the electron's antimatter particle, the positron, within the same framework. Similarly, all quarks and leptons have fields, and the fields couple and interact with each other. Amazingly, the three non-gravitational forces, electromagnetic, strong, and weak, change in strength relative to their energies. Vacuum fluctuations in space, which produce virtual particles, influence the properties of particles and their forces. There is always a cloud of virtual particles materializing in and out of existence, surrounding all particles in space. However, scientists have been able to perform calculations that indicate that given large enough energies, like 10 to the power of 14 giga-electron volts, the strength of all three forces becomes similar to each other. There is speculation that perhaps all three forces are really different sides of one single force, and the vacuum fluctuations in space make them appear different. This type of theory is what's known as a grand unification theory, or GUT. Interestingly, these gut theories make real testable predictions. For example, they predict the presence of new undetected massive particles called X and Y, which have energies upwards of 10 to the power of 14 giga-electron volts. These types of energies are far beyond what present-day supercolliders can produce. Moreover, gut theories also predict proton instability. They suggest that quarks can turn into leptons by emitting X and Y particles. However, this is incredibly unlikely, and some estimates predict the lifetime of protons to be around 10 to the power of 30 years, which is unfathomably long. I hope you enjoyed this episode, and remember, oddly real, really interesting.